Boom. So let's go back to the top. Look, you might started recording late. My apologies. Here we go. We're not very far though. So independent variable, dependent variable, scaling. Scaling is a big one. You need to choose a scale that makes the graph as large as possible on your page, but use reasonable increments. Let's talk about what reasonable increments are. Kiana, favorite pizza topping?
Cheese.
Love it. What kind of cheese?
What's this stuff that goes on a white pizza?
Like feta? Or like mozzarella? Mozzarella is your standard cheese. That's a standard cheese. Okay. But feta on pizza is good too. Feta is like that crumbly cheese that they put in Greek salad. Scales. When you choose your scale, whatever you choose for your scale needs to use at least half of the graph provided. The trees are dead. They have been sacrificed so that your learning may commence. Do not cram a bunch of graphs into tiny sections of the paper. I have graph paper coming out of forever. Wrong drawer. This drawer. This. This is all different kinds of graph paper. Different size squares. Some of them are big. Some of them are like absolutely standard graph paper. I really like these ones. I have lots of these. Because then especially when you look at it further away, you can see that there's a bigger square outline here. Like the lines are slightly darker at the 5x5. But there's normal size squares there. This is a good graph paper. This is the one that you guys are going to use for me today when you do your lab. I also have slightly psychotic graph paper.
Oh.
Students look at this graph paper. I'm a big fan of this graph paper. Yeah.
Ew.
But this is really good for measuring or for recording really, really fine data. Having really, really tiny squares, maybe this is a centimeter, so then every square there is a millimeter, so that you can actually get, because there's 10 of them. Or maybe you're doing fractions of mil, I don't know what you're doing, but you're like measuring very, very fine things. Having a graph like this, especially when you're drawing lines of best fit, and you need, because for a line of best fit, to find the slope of it, you're not using data points, if you recall from it. You actually need your line to go through the corner of a square, whether that square is big or small. The smaller the squares, the more likely it is that your line is going to hit one of these things. Because it is theoretically possible to draw a straight line on a piece of graph paper like this one and never actually hit a corner. And if that happens to you, you have no really good, reliable way to find the slope. It is possible to do. Much harder to do. Graph paper looks like this. It's dry. So you know what? You will make sacrifices for the sake of physics. Not for this course. You chose to be here. And so the sacrifices will be called upon. Okay, so we talk about making reasonable increments. What is a reasonable increment when you're choosing the scaling for a graph?
1, 2, 3, 4.
No. If you're gonna have a graph going up by ones, yeah, that's totally fine. Ones are fine. We like ones. One line is 1, the next line is 2, the next line is 3. It's what you guys did here. The scale goes 1 by 1. Going 1 by 1 makes it really easy to count. You just be like, oh, okay, I just count the squares to find the slope. You got to be careful, though, because I gave you this guy here yesterday, and a student who shall remain nameless to protect their identity said, I got different slopes when I counted the squares versus when I actually did the math. And that's, yeah, because they're different. The scales are different. The square isn't 1 by 1. It's 0.04 by 0.02. Like, it's the squares. Yes, it's a square, but the side lengths are different because the scaling on the graph isn't the same and doesn't have to be the same for the horizontal axis and the vertical axis. You need to pick scales that work independently of each other for both sides so that you use at least half the graph that's provided and still have a reasonable relationship between what you're graphing. So ones are good. Twos are okay because it's really easy to estimate half of 2. Half of 2 is 1. So, and when we say twos, I'm not even talking about like it has to go up by 2s, like 0.02, 0.2, all fine. If it ends in a 2, you know the halfway marker. If you're going up by 0.2, halfway is 0.1. If you're going up by 0.02, halfway is 0.01. Like, it's not difficult to do. Fours are okay. Sienna, you said 4. Fours are okay. Because you can break the square up into quarters. And you can reasonably estimate your way through that.
By 1, 2, 3, 4, and I go by ones.
Oh, you went 1, 2, 3, 4, so you're going by ones. Okay. But fours are okay too. Threes are horrendous. Threes are vile, and any multiple of 3 should never, ever show up on the scaling of a graph as the scale jumper. Going up by 6, yeah, on my scale, I'm going up by 6s. I'm not going to even read it. Just to make it truly barbaric, I'm going up by 27. Yeah, get out. Like at that point, it's just, there are numbers that do not scale nicely, that the in-between does not make sense, and that we as a race are bad at conceptualizing.
I'll make one just for you.
Okay, please don't. So these are good. These are bad. 3s are bad. 4s are okay. 5s are okay. Because even though half of 5 is 2.5, and then half of 2.5 is 1.25, for some reason, it does still work. But going up by 3s, going up by 6s, going up by 7s, things you all want to avoid. 8s are okay. But again, these are better. 10s, we like 10s. Or tenths, or hundredths. Multiples of powers of 10. Or not multiples of 10, powers of 10 are good. So there are good scales and there are bad scales to you. 3, 6, 7, 9, all bad. These are your golden children. These ones are the children that, they're pretty good. They're pretty good. But there are good and bad scales to choose to use. Your data points. Data points should be placed as accurately as possible on the graph paper. Lots of the mistakes that I see are because people are sloppy. They're rushing or they're trying to copy from their partner or whatever. They don't really want to be in physics, and so they're doing all their work as quick as humanly possible just to get it done. I'm not saying you have done that. You haven't done that yet. But this is what I've seen from students. They're like, it's just whatever. Graphic, get it done. No. You're here to learn things, to do things meaningfully. Data points need to be placed as accurately as possible. And if that means you have to be as neurotic as I have been in the past and be like, I really need to get this finally on there, I'm going to sharpen my pencil. Then by all means, do what you got to do to make sure that point is that point. And the fact that you have a dull pencil isn't like blotting out the issue. If you understand what I mean by that. Like you're not muddying the issue. And then this is where that we're going to really start to practice a whole bunch. Your best curve or best line, or the way we called it yesterday, I called the line of best fit, or the curve of best fit. You will practice what it looks like to draw your lines of best fit. Data points do not usually line up perfectly due to experimental errors. Draw the line or curve that comes as close to as possible to as many points as possible. That means there might be a 1 or 2, if you're taking 10 data points and 1 or 2 of them are really bad, you want to get as close as possible to as many of the points as possible. And yeah, you should let 1 or 2 bad data points skew you a little, but not as much as the 8 that are following the trend you're expecting them to follow, or that they look like they're trying to lead you down. But there should be a little bit of skewing towards something like an outlier because for whatever reason, it's there in your data. And I mean, if we can identify why the outlier is there and toss it, great. But often we can't do that. If the trend line is a straight line, use a ruler. I got lots of rulers and I got lots of straight edges. If it's not, some of the things that we're going to do, probably not today, but definitely tomorrow, I've got tools look like this. This is called a French curve. And a French curve is designed so that all the different parts of this curve, this curve, this curve, even down to here, are all different approximations of real curved functions. Whether they're exponential, or logarithmic, or parabolic, or cubic, or sections of cortex, they're all here. And so if that means you have to move the thing around to connect the line, or use the inside, or use the outside, these things come in a 3-pack for those of you who really want to draw the lines. There's all 3 of them. the number of different curves you can, I mean, it looks like a tribal tattoo almost. Like the number of different kinds of curves you can draw with this, and this comes as a set from Staples, with all of these different curves, still give you an entirely reasonable curve of best fit for given data. And everything we do in this class is going to have some sort of mathematical function that relates to it. If it's not linear, it'll almost certainly be parabolic or exponential. For at least, parabolic more likely than exponential. Yes, Andrew.
So, wait, you said something about all of the lines or curves, they're something for algorithmic stuff. So do they actually find functions and stuff that
Yes.
are commonly used and put it into a good form?
Yes.
How do you know which ones are which? Or is it just whenever you use approximate?
You use the curve that best lines up with the data you've been given.
Okay.
And then when you create your relationship, you'll be able to see how it connects and what the actual function is. They're not labeled on here because for some of these things, like this portion of the curve and this portion of the curve, even though it's one continuous curve, aren't necessarily the same mathematical function. So you use what works best for the data that you're looking at. And then, I'll model this for you over the next couple days. We're gonna spend the next couple days graphing, using rulers and these tools. Today we're gonna do linear. Tomorrow we're gonna break into these and start graphing curves. And I'll show you a technique called, which the 12s, the four of you, if you're in Pre-Calc 12 or have taken IB, that you'll be aware of. But there's ways to linearize curved functions by taking logs of things. Have you guys heard of logs? Violet has, Sienna has not. I'll show you, I'll walk you through that step today, and you'll see how curved data gives you taking a mathematical operator of a set of data, a whole set of data, will force them to show up in a straight line, and how that relationship can still be analyzed. It's really quite cool. It's a technique we use all the time in physics to analyze ridiculous data. Yes. This is a big one. And no matter how many times I say it, students seem to do it anyway. Do not just connect the dots. Even if your data isn't a straight line, if it looks like it should be trending towards a straight line, draw me this line of best fit. Same thing with the curves. There's a lab coming up where you're going to have curved data that you're going to take slopes of, that you're going to then draw or make a linear graph of the slopes. It's going to be great, but there's layers there. And for any of you who, you'll do this and you'll go off into calculus and you'll be like, oh, it's related. It's going to be great. Especially if you have calculus next semester, then you can come back and tell me how awesome that activity was. So I'm going to do one example for you. And then rather than getting you to do a bunch of bookwork today, I'm going to do one example for you, and then I'm going to get you guys to go collect a bunch of data and try and do this on your own. And we'll see how it goes. I've never done it this way before. I usually get students to do all the bookwork, and then we do fun things. We're going to go straight to the fun things. See how it goes. So I've got this data. I've got a data table that has the depth under the water and the pressure. What's independent? What's dependent? What do you control? And what changes as a result of what you're changing? The depth, you choose what depth you end up at. That's your independent variable. And the pressure at that location is your dependent variable. You bet. So we're going to put the independent variable down here. I'm not going to put independent variable. I'm actually going to put the variable that it is. You don't have to put the whole thing. This is just depth is fine. Depth is in meters in this particular case. The dependent variable is pressure. Pressure is not something we study a lot in high school. Pressure is usually measured in, there's actually three different units that we use for pressure. One of them is ATM, which stands for atmospheres. Atmospheres are the multiplier of pressure from what you're experiencing right now. You are sitting right now under the weight of 1 atmosphere. That's the pressure you're experiencing right now. As you go deeper, for those of you who have swum under the water, you'll feel the experience of it pressurizing your ears. Your ears will start to hurt. It's fundamentally similar to driving up into the bush. As you get higher, your ears are going to start to plug, and that's the reverse. The pressure inside your ears at that point is greater, trying to get out, and it's making your eardrums struggle. Going underwater is the same. The pressure inside is less than the pressure outside, and so your eardrums are still struggling. So these are all multipliers of what you're experiencing right now. Right now, you're at 1 atmosphere. We're roughly at sea level. Pressure is also measured in something called bar and something called pascals, but we're not using either of those right now. So this is pressure versus depth. That is a totally sufficient title. And now we're going to go ahead and graph this thing. We need to pick a scale that will use all of the data. So it's given you kind of a darker line on here, both there and there. So that's what we're going to call our axes. What should we go up by for depth? If we go 5, it's going to be 5, 10, 15, 20, 25. If we go up every 2 is 5, then we're going to have 5, 10, 15, 20, 25. Going up by 1 square is 5. Takes us exactly halfway. I want you to use as much as possible. And because we can, we're going to use it all. So I'm going to call every 2 lines 5. 5, 10, 15, 20, 25. And then what should our scale be on the pressure side? Sorry? 0.5? So that'll be 0.51, 1.52, 2.53, 3.54, and we have to go up to 3.5. That's entirely reasonable. Calling every 2 lines 1 or every line 0.5 vertically works. 2, 3, 4, which makes that 3.5 and 2.5, 1.5, and 0.5. Cool. And now let's plot our data as best we can. The first data point is 0 and 1. So at a depth of 0 meters, we're up here at 1. Point plotted. At 5 meters deep, we're at 1.5 atmospheres. At 10 meters deep, we're at 1.9. We don't have 1.9 on here, so let's ballpark it. We could say, okay, if that's that could be 1.6, 1.7, 1.8, 1.9. We can ballpark it and say, well, it's kind of like right there. At 15, we're at 2.4, which will be just under right there. At 20, we're going to be at 2.9, which is right there-ish. And at 25, we're going to be right up there at 3.5. If you need a straight edge, grab one. Let's draw a line of best fit. Like if you look at the rulers, are always up at the front table. If I zoom in here, if I wanted to draw a straight line between any 2 of these data points, you're going to see that there are some data points that are going to be slightly low. Like if I just looked at the first one and the last one, these 1, 2, 3 points are low. If I look at these 3 middle points that look like they're kind of in a straight line, that point's going to be high. This point's going to be bang on. And so what we want to do is we want to draw a line of best fit that mimics all of these things. Now, these 3 points, that guy there, and that guy there, all kind of look like they would show up on the same line. Oops, sorry. I need to zoom out just a smidge. So I've got 3 points on here that look like they would form a straight line right through all 3. I've got another 3 that would form those same 3 lines. And so I've got kind of an equal weighting here. So what I'm going to do for my line of best fit is I'm going to draw it's going to be the same slope, and I'm just going to kind of slide it down here a little bit and go right through everything. Something looks like that. And so that thing doesn't actually go through any of my data points. It's close to that one. And so now what I want to do is I want to find the slope of this data, because we want to find the relationship that exists here. So, well, this one's going to be tricky because we have managed to draw a line that does not go through any corner on this thing. So we're going to have to ballpark this guy a little bit. What is a good point you think we could pull off this graph? It's not ideal. What could we do? Look at your line. What's a reasonable coordinate that you think you can pull off yours? Like if I do some estimating, this guy right here is not one of my data points, but it looks like it could be like a 0.4. I guess in this case it would be 2.5, 2.6, 2.7. Like that looks like something I could use. I can reasonably estimate that. I'm going to call that point, what is that? Halfway between 15 and 20 is 17.5. And what's that going to be? 2.5, 2.6, 2.7. Maybe that's the data point that I'm going to use there. I need something similar somewhere else. What if I go here? 1, 2, 3, 4. It's the same kind of vibe, right? It's that guy there. Maybe that's going to be 2.1, 2.2 in the y direction, the pressure direction, and what is that? 12.5. Even though my numbers are a little skewed because of the way I've drawn my graph, this is the relationship that I seem to be getting. So then let's do the slope right on there. The calculations you do should be done right on or next to the graph paper. So then the slope here is going to be, what's my rise? I'm going from 2.2 to 2.7, so that's 0.5. My run goes from 12.5 to 17.5. So that's a slope or a run of 5. So 0.5 divided by 5 is 0.1. So then the relationship that we're going to get between pressure and depth should look like this. When you're writing out your equation, we're going to line it up with y equals mx plus b. So for a while, let's practice that. Y equals mx plus b. Y is pressure. So the pressure value you get is going to equal 0.1 times your depth plus your y-intercept, and the y-intercept here is 1. Well, it looks a little bit lower than 1. But we know that 0, 1 is a data point. Let's use it. We were given a y-intercept. Pressure and a quick Google search will reveal that the relationship between underwater depth and pressure is that the pressure increases by approximately 1 atmosphere for every 10 meters of depth. Is that what we've figured out here based on our equation? This is, if you look at the let's go back and look at the units on this slope. 0.5 was your rise, that's measured in atmospheres per meter. So this is 0.1 atmospheres per meter. Google says 1 atmosphere every 10, and this is 0.1 atmospheres every 1. Is 1 every 10 the same as 0.1 every 1? Yes, it is. 0.1 atmospheres per meter is the same thing as 1 atmosphere every 10 meters, because this is 1/10 of a meter. Sorry, 1/10 of an atmosphere. per meter. So 10 of these would be a full atmosphere. So what we have found, given the data that we plotted and someone measured somewhere and we plotted the thing, we found that, and this is the steps that I want you to go through. We have found that this data aligns with what, at the very least, Google's AI says that the internet says is the relationship between pressure and depth, which is great. Questions about the procedure I just went through? I'm hoping it was not abundantly difficult, but there are technical things that I want to make sure you get. So, it is 12:20. There are 40 minutes left in the block. Rather than go through a bunch of exercises right now using cooked data, which you will have time to do later, what I'd like to do is first get you guys to collect some data of your own and do some graphing with the relationship that you know already. You should know it. Some of them have forgotten. I have a bunch of spherical and cylindrical objects in your homework for yesterday. Hopefully you did it. Was to bring a spherical or cylindrical object, or circular, spherical, cylindrical. I see a few. There was a, what is that? A socket. We have a little ball, which might have to be that same little basketball. I don't know if we're going to use them, but I see a water bottle there. What other circular, spherical, cylindrical objects do you have? Ooh, please don't use that in the glass. No, leave it out. Yes, but I don't want you spraying it places. Deodorant bodies for sure, love it. And I have a few that you're going to use too. So all of you, you can do this in 2s or 3s. You will never do labs in groups of 4 or greater, but 2s or 3s are acceptable. What I want you to do is all of you are going to use my objects, plus whatever objects your individual partners brought, and if they forgot, you can beg and plead, groups around you, find someone who did actually bring something. What you're going to do is you're going to measure the circumference and the diameter of a bunch of different circles. Some of these circles will be easy. I have a coffee can. There's actually 3 different circles now. There's a few different circles you can measure on a coffee can. You can measure circumference of diameter, pick one, whether you choose the inside one, the outside one, careful. Some of these, they're not that sharp, so you don't hurt yourself. Coffee can, diameter, circumference and diameter. Volleyball, circumference and diameter. This is not going to be easy. A globe, circumference and diameter. I'll even pop it out of here for you. Come here, you. There you go. Easier to use now. The Earth, as it was back in. Oh, Czechoslovakia already. What else we got in here? Yeah, no, that looks pretty good. Is Sudan one country or is it 2 countries? Yeah, no, there's problems on this globe. My pen holder, pick a circle. There's at least 3 of them. A funnel. I got a funnel. A whiteboard pen. So you've got 6 objects here. 3, 4, 5, 6. And the ones your group brought. Circumference and diameter. Now, it's going to be difficult to measure circumference using the tools that I have available to most of you. Because I don't have enough tape measures to give you all of them. And it's going to be hard to measure diameter of a spherical object using a tape measure. So you're going to have to play with and agree as a group how you're going to take some of these measurements. I'll provide you all of the tools I've been providing all semester. You've got some smaller rulers. You've got the meter sticks. I'll bring those out. I've got the tape measures. If I ask you to measure a curved surface using a straight line, what other tool might be useful?
Oh, bring in a ruler.
A string. Paul, brilliant man. So I have string, boatloads of it.
Dude.
You bet. Loads that I now have to pick up. Oh, you know what? Grab one of those and toss it in the middle over there. Yes, I have string. If you would like some string, it's right here. If you might find that useful, there is string. There is I have 2 different globes that you can do. String and scissors. There you go. That's an easy way to measure circumference. You lay the thing out. You make a mark on where it is going to be, but I mean, cut your own length so you're not using the entire roll while you're going. I want you to get what is the handout. You get a handout. Thank you for picking up all the globes that I
Oh,
brought.
wow. Over here.
Oh, you have an object then? There you go. You're working in groups, but you're all reporting your own data. Two, three, 4, 5, 1, 2,
It's your fault.
3, 5. Okay, you all got the handouts, the purpose of the lab. I didn't write the things down. I want you to figure out the purpose of the lab. Write something there for the purpose of the lab. The purpose of the lab is to find the relationship between the circumference and diameter of a circle. The purpose of the lab is to find the relationship between the circumference and diameter of a circle. When it says apparatus and materials, write in what you're actually using. Not everyone's going to use the same things. Not every one of you is going to use a meter stick. Not all of you might have to use the string. Write out what you're going to use. Don't worry about the, well, you can say the procedure. Don't worry about the procedure. We'll figure that out later. And then your data goes in that table there. Write the name of the object, write the circumference that you feel like you've measured, and the diameter that you felt you've measured, and there's spots there for 8 things, 2, 4, 6, 7 things. 7 things. And then you're going to graph. When you're ready to graph, I've got graph paper available for you. You guys are going to calculate your percent error. How could you calculating percent error is, we'll talk about it again further once you get to that point. But your percentage error is basically what percent are you off by in your relationship. Vikram, stop writing these down, please. What is the relationship between the circumference of a circle and its diameter? You learned it in elementary school. What's the relationship between the circumference of a circle and its diameter?
What?
What's the relationship between the circumference of a circle and its diameter?
Radius times 5? I don't think it.
Circumference is equal to, should be equal to, pi times the diameter. So, when you graph these things, the circumference is going to be your dependent variable, the diameter is going to be your independent variable, and the slope of that line should be what value?
Yes.
Y equals mx plus b. What should the slope of the line be for what you guys are about to do? Pi. We know that value, 3.1415926, whatever, goes on forever. So when you are ready to calculate your percentage error, what you're going to figure out is what percent are you off by, because what you're doing is you're calculating pi through this activity. So that is for tasks. Find your partner. When you're ready to start graphing, let me know. I'll provide you with graph paper. Give her step. Give her. Okay.
Oh, you even picked up the thing and put it back.
Alright. So that one,
Yes. The tapes are gone, it looks like. So I would recommend straining these before these guys disappear. That would be a good one. This is not a bad one. You're using string, I recommend one.
Yeah. Yeah, but that's what I am.
Make sure you're sharing my items.
I think that was.
And all of the items in my items need to make their way back to that table at the end. There's the coffee can, the funnel, the whiteboard pen, 2 different globes.
What is it?
Okay, for those of you who may have forgotten what you're trying to measure, there's a circle-ish. Diameter is the distance edge to edge through the center. That's your diameter. And circumference is once around the outside.
There we go.
Around the outside.
You need to divide
Around the outside.
Oh.
And make sure your partner's involved in the process. Nobody gets a freer eye.
Wow, I love this. This is very nice. Oh, wait. It's just 2 diameter. Yeah, so much easier. Oh, it's. What's the next
Oh, I don't
Okay. Sorry? All of them. Fill the table. Fill the table, yes. All the different items. Yeah, guys, you're filling the table. You're not doing one item. Do one item, and if it's mine, return it to the table so another group can grab. You're filling the table. 8 items. At least. That you're grabbing. 7 items. At least that you're grabbing for this. Oh, wait, there's another one. Globe.
Oh, actually, that'd be okay. Ready? Oh, that's the new one. Yeah, Yeah, let's see, is my country on here?
Sorry?
Break it apart.
No, do not break my... No, you may not break any of my objects. Figure out how to measure the diameter of a sphere. Figure it out. There are all sorts of creative ways you can measure this. For no reason in particular, I'm going to place these two longerish pieces of wood here at the table. Tools you might want to consider using. You might not need them, but you know, if you're a creative, enterprising thinker, you might be like, "Oh, this could be useful for measuring diameters of things." That is the equator. That would make sense.
Yeah, it's longer than the cooler.
Sorry? Ask your partner. Then you can go. Write your name on the board. If he's cool being left alone, and if you trust him, then go by all means. Yes.
For the ball, like the volleyball, would the circumference and diameter be the same?
The distance across the circle and the distance around the circle are never going to be the same.
Because it's like a ball.
The distance across the center and the distance around the outside will never be the same. Because the relationship is the circumference is equal to pi times the diameter. So you're always multiplying the diameter by something to get to the circumference. No, it's never the same.
100 plus.
It's not. Hello.
So I have a problem.
Yes. Okay.
So I didn't understand this one. Like, how can you do like 5.0 of this grid? Like, how did we find this one?
So your graph isn't the same as mine. Oh, that's 20. That's 25. How did I? No, 5. I mean 5.0. That's. Oh, you also didn't start at the same spot I did. I went over 2 and did 5, and then over 2 more for 10, 2 more for 15. You went 1 for 5 and then 2 for 10. So your scale jumped. Don't use it, guys. No. Measure and then return. We're not playing volleyball. Measure and return. What was the noise? Okay. What did you just do for diameter? Your diameter is through the center. Through the center. You cannot use the curved part. You cannot use the curved part. Figure it out. No. Figure it out. You guys have to figure out a way to measure the diameter of a sphere. Get creative. Again, diameter is the straight line distance through the center of a circle. It's a straight line. Diameter is a straight line. So what I did for here, ask your partner if you're okay with them if they're okay with you leaving. Do you trust them not to screw around with the lab while you're gone? Then by all means, go for it. So then I just estimated. I said, okay, well, that's 2 and that's 2.5. Then I made some. I broke it up into what I thought were reasonable estimates, chunks, 5 chunks. So that would be 2.1, 2.2, 2.3, 2.4, 2.5 is estimated. And then I found the slope using my estimate. Does that make sense? Yeah. That's what happened.
I just realized. If I'm measuring something like this, the diameter, people don't find that it's half straight line. All these diameters.
Oh, yeah.
Yeah.
Since we've been doing, I mean, they did what this. So it's
Okay. This is in this handbook.
I just live in where are you from? India. Yeah, what is the
Here you go. Here's something for you to measure.
What would you like to use? What? Sure.
Yeah. I only want flat circles, not.
No. You have to do spheres.
We did spheres.
You measure the diameter of a sphere?
Yeah.
we just did backward math.
Yeah.
No. You have to measure. No backward math. No. I want you to measure. You get nothing. Get out of here. Measure everything. No backwards calculating. No, you may not use it. Go away.
Look at the making.
Yes. Measure the diameter of the spheres.
Can they just do this downstairs? I'll show you.
No, that's different.
That would be like flat though. That's how.
No, that's not how that would work.
I'm just gonna spray.
Get creative. Especially that globe. There's a hole right through the middle of it.
Oh, we got.
There's a hole at the top and a hole at the bottom.
Oh, no.
No, guys, this table, you are measuring everything. You are not reverse calculating anything. You are taking measurements. You are measuring the circumference, and then you are measuring the distance from side. You are not. There's no calculations going to making this table. Oh look, they're using the things I provided. Really fascinating. Okay, maybe you could use. Oh, later.
Oh, wait, I see.
Seneca, or whose ever idea that was.
Hey, can you give us a globe?
Fascinating. I have two more. Yeah, there's yeah. You can grab another one of those globes, and I have more sticks. Should anyone want to do what Seneca's doing? There's 3 more sticks on the couch.
I have an idea. It might not be.
3 more sticks on the couch.
No.
If you want to use them, go for it.
Let's look at it.
Something like that. But that's gonna be a lot harder. So you need sticks that you have to square on their phone.
You think it will? I can use it.
See, the beauty of these, if you're really careful, is that they will actually stand. Stand without you aiming. Yeah. So now, the more you do about probably got there's a string that's curling. Okay. But this is also an option.
Yeah, go on. I have an idea.
Okay.
Sitting right now. Like a basketball.
No.
Go. Is it weighted enough?
Oh, top is a, I have one. I have. I'm not gonna like it.
The which, sorry? You ready to start graphing? You've measured all of the things
not all the things on this table, but I have measured all of the swaths.
7 things.
Yes.
Okay. When you are ready to start graphing, up here at the front, we're going to use the teeny tiny. There you go. Okay, we're using the teeny tiny graph paper.
Oh.
The diameter needs to be your independent variable. The circumference will be your dependent variable.
What did it get? What did the slice out there?
Up the front.
What defines the way?
Assume that there are things to do when that flash is probably not going to be okay. You're in the round. It's not my fault. Because we started that round in my class. At no point should you be in the round. Now, if you started it at lunch, and you're like, we don't gotta finish, well, that's fine.
What can you do?
Now you have the consequences, and I'm going to lose that round. How do I read the consequences?
I think it's on the line.
Not be on your phone.
Oh.
So
You have a task to do. That is provincial policy, not mine.
That's the height. We did it.
I have to take it away.
Oh, is it done?
Yeah.
Okay.
It's exactly what we want.
Fantastic. No, I got lots of
It's
students.
exactly what we got. Yeah. Yeah. What'd you get for your? That felt way more complicated than it needed to be.
Yep.
Oh well.
Measuring the diameter of a sphere is not an easy thing to do.
I can see that.
It's a hugely irritating thing to do.
Me and Violet just engineered for a race.
There's a tool that exists called a caliper that's what it's designed for. Yeah. It's basically what a caliper is it's basically 3 of these. One is locked in. I've already removed it for a second. And the other one sits square to the first. You have a wheel that you use. You slide this thing in until the sphere is at its widest point. And then, well, some of them are digital, some of them are analog. Digital ones will have your it's effectively what you guys did. You have your caliper. It probably just went up and moved them over. Thing. It is not time to pack up yet. None of you should be packing up.
We're gonna get your paper towel.
At the very least, all of your measurements should be taken before you go. And I want all my stuff back. Please. Okay, so you do not need to finish this for homework. You will have time tomorrow to work on it. Yeah. Oh, no. You're that guy. No. Class. None of my tools return them. You have to know. The next four keep on. If you are done all of your measurements and would like to pack up, now you can.
So when they find us, anyone needs on, but they were on to get.
Take all your measurements before you leave.
I get it.
All measurements taken before you go.
I want to just do voice. I was wondering. Choose this.
You're in leadership?
Last for student voice. I'm sorry, grad council.
No, it says you said here that you were in leadership.
Oh yeah, I'm in leadership. Be leadership. Yearbook.
Oh, I just asked you if you were. You said no.
Sorry. Yes.
You're in leadership.
I thought you were saying like, is this leadership?
No, I sorry. Oh, this is grad council, not student voice.
Yeah. I keep saying student voice. It's just.
Are you on student voice?
Yeah.
You're on that too?
I've been a lot.
Do it.
Thank you.
I affirm your choices. Okay.